Welcome to Electron Control. Today we're going to look at discretizing a continuous time system and also various useful inputs. So the key learning points. I hope after today's lecture you can explain the process of obtaining a discretized system and also how to undertake the process, and also explain the various inputs that we can use. So on this slide you should be familiar with the illustrations. So on the top one, this is how, in terms of theory and simulation, what we do is we multiply the zero to hold and the continuous system in the continuous domain, so G subscript ZOH of S multiplied by G of S, and we undertake the Z transform of that to determine G of Z. Okay, and that's developing a discretized system model that we can use within the sample data control system that you saw in the previous lecture slides or lecture video. In practice though, however, the zero to hold would be located within the microcontroller or microcomputer. So last lecture we discretized the numerator of the zero to hold, and we were left with 1 over S, which was the denominator of the zero to hold multiplied by G of S. So just to get you familiar with using the tables of transforms again, so in previous years, when we looked at continuous control, we would have converted from the time domain to the S domain. We also would have taken inverse Laplace and converted back to the time domain. So now what we're doing is we're going to take a continuous transfer function and convert it into the Z domain. Okay, these are known as Z transforms. So here you can see the Z transform of 1 over S plus 2 becomes, when you undertake the Z transform, becomes Z over Z minus e to the power of minus alpha ts, where in this case alpha is 2. Row 6, you can see similar idea. So in this case, row 6, continuous transfer function here where alpha is 5, and you can see the transformation here into the Z, undertaking the Z transform, where this case here, this alpha here is 5. If we now then look at this Z transform, so 1 over S, then in brackets S plus 2, close brackets, and then brackets again S plus 3, close brackets, you can see that this is not in the standard tables. Okay, the closest is perhaps row 12, ID row 12. However, this is not in the standard tables, so we can't directly use the tables to transform this into a Z transform. So what we have to undertake is partial fractions that breaks it down then into functions that then enables us to use the tables of transform. So the tables of transform saves us a lot of time because it saves us from doing the mathematics when we transform from one domain to the other. So discretizing a continuous time system. So there's 4 main steps. The first step I spoke about, so partial fractions. So when we've got a transfer function that we can't directly use the tables of transform, what we have to do is break it then down into the partial fractions. So here you can see some common partial fractions that you would expect to use. So when you've got real poles, so in this case S plus A, that the partial fraction that you use is A over S plus A. Okay, 2 equal real poles, so S plus A squared, you use this partial fraction expansion here. 3 equal poles, this one here. Okay, I'm not going to go too much into detail in this because this is something that you would have studied previously. And then here when you've got a real pole and 2 complex poles. But in this course we won't cover when we've got complex poles. So where A, B and C are unknowns. And what you're trying to do is effectively determine what these A, B and C unknowns are that then enable you to use the tables of transform, which is the next step. So once you've kind of determined the partial fractions, then use the tables of transforms to convert from the S domain into the Z domain. And then we form then a common denominator, because what we'll have is different different functions. Then what we want is a common transfer function. And then step 4 then is to multiply by the zero to hold numerator. So this is what we saw in the last video. So this is where we finished off in the last video. Okay, when you had z to the minus 1 over z, which is the numerator of the continuous zero order hold, and then 1 over s, which is the denominator, the s, and then the z transform of 1 over s g of s. Okay, and that's effectively what we're trying to achieve. So let's get on to a question. That's probably the best way to understand the process better. So in this example 1, we've got a sample data control system that is designed with a sampling interval ts is equal to 1 second. The open loop system transfer function is given by this. So g of s is 12 over s brackets s plus 2, close the brackets, and then brackets s plus 3, close the brackets. It's got a zero order hold with a transfer function of this. That's the form that you're going to see quite often. Well, you're going to see continuously for the zero order hold, and then by making use of g of z is equal to this equation that we just saw, show that the z form transfer function of the open loop system is given by this. So effectively using this continuous transfer function, the zero order hold, and we previously discretized the numerator and just left with the denominator, subject to a sampling interval of 1 second, arrive at this. Okay, I've also given you the partial fraction expansion. So here you can see, if you look at the original transfer function, s plus 2, see that these are just your real partial roots, s plus 3, and then s plus 3 here. Recall that you've got this 1 over s multiplied by g of s, hence where the a over s comes from. So then if I'm moving on then to running through the steps. Step 1, so using partial fractions to allow the tables of transform to be used. So first of all, what I'm just doing is just rewriting out the equation, and that I've gone over a couple of times, where g of s in this case is 12 over s plus 2, s plus 3. Okay, what I'm going to do now is write out the partial fractions. So that transfer function is equal to a over s plus b over s plus 2 plus c over s plus 3. What I'm going to do is cross multiply by the denominator, and here, sorry, there's an s missing there. There should be an s there, and if I cross multiply that, obviously that there, if there's an s here, is going to cancel, give you 12. The s is going to cancel, so you can have a s plus 2, s plus 3. The s plus 2 and s plus 2 are going to cancel, so you end up with this. S plus 3 and s plus 3 are going to cancel, you end up with this. Then what I've done here is just factorised out this, this, and this. So you see s squared plus 2s plus 3s, so 5s plus 2.6. So what I'm going to do now is equate the coefficients. So looking at the terms where s is 0, so we've got no s term, s1 and s2. So if we look up here, there's no s term, so 12. 6 has got no s, so 12 is equal to 6a. Therefore, a must equal to 2. So if we're looking here at the terms with that correspond to just an s term, so it's 5, 3, and 2. So 2a plus 3b plus 2c. We've got two unknowns still though. And then s squared there, there, and there. So a plus b plus c. What I'm going to do then is multiply this by 2. Okay, so you can see there I've multiplied that line by 2. And then I'm going to subtract that from the terms that correspond to s1. And you'll see why I'm doing that, because it enables me to effectively get rid of these c's, two c's, and then to determine what b is, because I know what a is. So in this case, b is equal to minus 6. And then from that, I've determined two knowns now, so I can work out the final one, so using s squared. So effectively 2 minus 6 plus c is, it's equal to 0, therefore c is equal to 4. So I've got now my 4 unknowns, so my a, b, and c. So the partial fractions are given by this, so that's your transfer function. So it's equal to 2 over s minus 6 over s plus 2. So that's an s there, weird looking s. Plus 4 over s plus 3. So that is your partial fractions. So what we can now do is use the tables of transform, where we can convert from the s domain to the z domain. So you can see here for this we're going to use row 3, and here row 5 and row 5. So I'm just going to rewrite this, so the z transform of this expression here, and then undertake it. So you can see what I've done. 2, move that outside, move 2z over z to minus 1, minus 6, move that outside, z to the over z to the minus e minus 2ts. Okay, so there's a 2 there, you can see the alpha, and then repeated the same for this. What I've done is taken z out as a common factor. So in this case we end up with 2z, multiply 1 over z to the minus 1, minus 3 over z to the minus e minus 2ts, plus 2 over z to the minus e minus 3ts. So now we've got that converted into the z domain. So now what we want to do is form a common denominator. So what we're going to do is on the denominator we are effectively going to put all 3 of the denominators from these 2 fractions up here. So 2z, z minus 1, z minus e to the minus 2ts, multiplied by z to the minus e minus 3ts. And then what we're effectively going to do is work our way across. So if we just wanted 1 over z minus 1, what fractions would we have to put here? So it'd be these 2 effectively. So if we put these 2 up here, then they would effectively cancel with them, then we'd just end up with 1 over z minus 1. And then likewise, if you move to this one, which 2 would we want to, which 2 would we need? So it'd be z minus 1 and z minus e to 3 to ts. And just remember this 3 here, okay? So we need to keep the 3. So 3 z to the minus 1, as I said, z to the minus e minus 3ts. And then finally, if we're looking at z to the minus e minus 3ts, what it's going to be is effectively these 2 here on the numerator. And again, just remember the 2. And that there is your common, there you've got now a common denominator. So the final step then is to simplify the transfer function first of all, and then multiply by the zero-hold numerator. So just recall that when you multiply 2 exponential terms, so e to the n, multiply e to m, that equals e to the n plus m. So what I'm doing is just multiplying this out now, so z squared, this multiply this exponential multiply z, this then multiply by z. Obviously z's common, so I can put that outside the brackets. This multiply this ends up being e to the power of minus 5ts, remember this. And then just exactly the same follows through for these. Okay, this can get a bit messy when you're working your way through this, so just be careful. And then the denominator is as it was before. So we'll just write that out as it was before. Okay, what you should notice is that you've got this z squared, 3z squared, minus 3z squared, sorry, and plus 2z squared. So that's just something you should always notice, that the z squares cancel. Okay, what we're going to do now is further expand this out. So 3, we got a minus and a minus, so 3, 1 plus e to the minus ts, take away this, effectively these here, and then take away, there you've got a plus there and a minus, so 2 multiply 1 plus this exponential minus 2ts. And then what then I've got here then is just all these exponential terms that are on their own. Okay, and again, same denominator, sorry. And then what I'm going to do then is rearrange to move z to the minus 1 outside, effectively move this outside the bracket, and I'm going to substitute in ts, because the sampling interval here, ts, is equal to 1. Okay, so just get your calculator out and put this in there where ts is equal to 1, and you should end up with something that looks like this. And just recall I've moved z to the minus 1 outside here. So here is your transfer function. Now I'm going to multiply it by the 0 to hold numerator. So this is what we had at the beginning, z to the minus 1 over z. And what you'll notice is this z to the minus 1 and this z to the minus 1 cancel, and this z here and this z also cancel. So you effectively just ended up this 2 here that's going to multiply by the numerator. So here I'm just writing out the final form of the transfer function, so 1.372z plus 0.52561 over z squared minus 0.1851z plus 0.0067. And that there is your g of z, so your discretized transfer function. And what I'd say is I'd advise watching the MATLAB video afterwards, because you'll see how this transfer function here, how it relates to the continuous transfer function. Because effectively what you're getting, if you look at your continuous transfer function, you simulate that, you'll see a continuous signal. Your g of z, you're effectively capturing information from the continuous transfer function every ts seconds with this transfer function, which in this case the ts was defined as 1 second. So just a quick exercise for you to now have a go. So what I'd advise is that you pause the video for 15 minutes and work your way through this exercise. You'll see the structure of the question is the same as previous, and I've given you the same sampling interval 1. The only difference in this question is the continuous transfer function. Obviously that results then in a different g of z. The form of the partial fractions is the same. So have a go at that, pause the video for 15 minutes. So the final part we're going to go over in this lecture now is useful inputs. So the step input or the unit step input will be the input or reference that we mainly use. So in the case of a step input, the continuous domain, you should have been used to seeing capital U of S is equal to A over S. Where in the case of a step input, you can define A, any given value. Looking at the tables, this transforms to Z over Z minus A. In this case, in the tables, the table here gives me a unit step input. So in this case, 1 over S. So a unit step input where A is effectively 1, and then that then transforms in the Z transform in the Z domain to Z over Z minus 1. Okay, where you can see the 1 here is effectively what would be your A if you just looked at step input, and what would be your A here. And you can see here when it's been applied in the time domain, so here you can effectively see it's just a step change, where here the magnitude is A, and in this case with the unit step input is 1. So some other useful inputs, so impulse, so you're looking at row 1, this is effectively just a 1 being inputted to the system, and a sine wave. So you can see here a sine wave in the time domain, so you should be used to that, in the S domain and then the Z domain. In terms of this, I won't worry too much about the mathematics, because a lot of the time, if we put a sine wave in, we'll just be using the source block within Simulink. A lot of the time, we'll just be using the step input or a unit step input. So I hope in this lecture that you've understood the process for discretizing a system model, so capturing g of z using a 0 to hold. Okay, so the last lecture we got the numerator of 0 to hold. This lecture we've multiplied 1 over s, which is the denominator, multiply that by the continuous transfer function, and then we've developed then g of z based on that. This is developed for within a sample data control system, because what we're trying to do in the model is we're capturing information at the sampling point. So watch the previous video if you don't quite understand sample data control system and understand that G of Z is trying to capture information at the sampling point, and watch the next lecture, because what that's trying to do is to kind of show you visually, we use exactly the same steps, but we use MATLAB to investigate different sampling intervals, which captures obviously varying differences in terms of information. And what I've also showed you is various useful discrete inputs have been introduced, such as step input, unit step input, impulse, and sine wave. So I hope that leaving this lecture that you've understood the process. Now you know how to discretize the system and undertake that process, and you also understand some useful inputs that we'll be using in the coming lectures. If you've got any questions, please email me. Thank you.